Welcome to Mathematical Analysis. Today we are going to explore one of the most powerful tools in all of mathematics, Taylor series expansions. Imagine if you could take a complicated, impossible to calculate function and perfectly rebuild it using only basic addition and multiplication. That is exactly what a Taylor series does. And by the end of this video, you will understand exactly how it works. Now that we know our goal, let us understand the core idea. Think of a master tailor making a custom suit. They do not measure every single millimeter of your body. Instead, they take detailed measurements at a central location, like your waist, and extrapolate to build a suit that fits perfectly. In mathematical analysis, a Taylor series does exactly the same thing for curves. It takes measurements of a complicated function at one specific center point, recording its height, its slope, and its curvature. Using just that localized information, it builds a perfect mathematical replica of the entire function out of simple polynomials. This is incredibly powerful because polynomials are easy for us and computers to calculate. So, how do we actually build this mathematical replica? This brings us to the master formula for the Taylor series. Conceptually, this formula adds up an infinite number of terms to wrap a polynomial around our original function. Let us break down the symbols. The f of x on the left is the complex function we want to approximate. The sigma symbol means we are adding up an infinite number of terms. The numerator, fn of a, represents the nth derivative of the function evaluated exactly at our center point a. The denominator is n factorial, which naturally arises from repeatedly taking derivatives of powers. Finally, x minus a to the power of n is the building block that shifts our approximation to the chosen center point. As we add more terms, the approximation gets better and better. Before we look at why this formula works, let us see it in action with a concrete example. We are given the natural logarithm function and we want to find its Taylor series centered at a equals 1. We cannot center it at 0 because the natural logarithm of 0 is undefined. Our first step is to calculate the value of the function and its first few derivatives at this center point. The original function at 1 is 0. The first derivative is 1 over x, which evaluates to 1. The second derivative, using the power rule, is negative 1 over x squared, giving us negative 1. The third derivative becomes 2 over x cubed, which evaluates to 2. We now have our specific numerical measurements for the height, slope, and curvature. Now that we have our derivatives, let us plug them into the master formula. We substitute 0, 1, negative 1, and 2 into the numerators. Notice that every term contains x minus 1 because our center point is 1. Next, we simplify the fractions. 2 factorial is just 2 and 3 factorial is 6, so 2 over 6 simplifies to 1/3. This leaves us with our final polynomial. If you plug in a value close to 1, like 1.1, this simple polynomial of addition and subtraction will give you a highly accurate decimal value for the logarithm without ever needing a calculator. We have successfully turned a complex logarithm into basic arithmetic. To truly understand what we just calculated, let us look at this visually. Here is the graph of the natural logarithm in black. At our exact center point of x equals 1, all the approximation curves perfectly intersect the true function. The first degree approximation in red is just a straight tangent line. It is accurate only very close to the center. The second degree approximation in blue is a parabola that captures the initial curve. By the time we reach the third degree approximation in green, the polynomial hugs the true function tightly over a much wider stretch. As we add more terms, the polynomial wraps closer and closer to the true shape of the original function. Let us solidify this with one more practical example. Suppose we need to approximate the square root of 4.2. We can do this by finding the Taylor series for the square root of x centered at a convenient point, a equals 4, where the square root is a perfectly known whole number. We start with the base function, which gives us 2. Taking the first derivative using the power rule brings down the 1/2, and evaluating it at 4 gives us 1/4. Taking the second derivative brings down a negative 1/2, and evaluating it at 4 requires calculating 4 to the power of 3/2, which is 8, giving us negative 1/32. Continuing with our square root approximation, we plug these evaluated derivatives into the Taylor series formula. Because our center point is 4, the polynomial building blocks are powers of x minus 4. We then simplify the complex fractions by multiplying the denominators by the factorials. This final polynomial allows us to estimate square roots near 4. If we plug 4.2 into this polynomial, the x minus 4 term becomes 0.2. This makes the arithmetic incredibly easy to do by hand, yielding a highly accurate approximation of the true square root. You can see how powerful this is for numerical estimation. Now that we have successfully used the formula, let us understand where it comes from. We must derive it step by step. We start by assuming that our complicated function can be represented by an infinite polynomial centered at the point A. We write this polynomial using unknown constant coefficients C0, C1, C2, and so on. Our goal is to figure out what these unknown constants must be. To find the first unknown constant, C0, we want to eliminate all the other terms. We do this by evaluating the function exactly at our center point, E. When we plug in E, every term containing x minus E vanishes into 0, leaving only C0. So the first constant is simply the height of the function. This chunk of the proof establishes how we find the subsequent coefficients by looking at the rates of change. To find the next constant C1, we take the first derivative of our entire polynomial equation. The constant C0 disappears and the power rule brings down the exponents on the rest of the terms. Just as before, we evaluate this new derivative equation at our center point. All terms containing x minus a vanish, revealing that C1 is exactly equal to the first derivative. We repeat this logic for C2 by taking the second derivative, which represents the curvature. The C1 term disappears and the power rule brings down another multiplier. Let us conclude this derivation. When we evaluate the second derivative at our center point, everything vanishes except the C2 term. Solving for C2, we get the second derivative divided by 2 times 1. If we continued this process for the third derivative, we would divide by 3 times 2 times 1. This multiplying pattern is called a factorial, denoted by an exclamation mark. This reveals the universal pattern for every coefficient in the series, the nth derivative divided by n factorial. By substituting this general pattern back into our original assumed polynomial, we arrive exactly at the formal definition of the Taylor series we used earlier. The intuition is beautiful. Matching derivatives guarantees the polynomial mimics the function perfectly. So we have proven that the formula holds, but this brings us to a critical warning. A Taylor series does not always work for every possible value of x. Think of the center point like a flashlight shining in the dark. The light is perfectly bright exactly where you are standing, and it illuminates the ground for a certain distance around you. But eventually the beam fades into total darkness. In mathematics, the distance that this light reaches is called the radius of convergence. Within this radius, the infinite sum will converge, meaning it settles down to perfectly match the original function. But if you plug in an x value outside this radius, the series diverges, blowing up to infinity and producing complete garbage. Beyond the radius of convergence, there is an even more dangerous trap. Sometimes a Taylor series converges perfectly to a finite number, but that number is completely wrong. We call a function analytic if its Taylor series actually equals the function itself. However, there are smooth, non-analytic functions where the series exists but fails to describe the function anywhere except at the exact center point. A famous example is e to the power of negative 1 over x squared. This function is incredibly flat near zero. Every single infinite derivative at zero is exactly zero. So the entire Taylor series just equals zero. But the actual function slightly rises as you move away from the center. Having all derivatives does not guarantee a successful reconstruction. Despite these caveats, why is this so important? Taylor series expansions are the hidden engine running inside almost every modern computational device. When you ask a calculator to find the sine of an angle or a logarithm, the machine does not actually know what those functions are. Computers can only perform basic arithmetic like addition and multiplication. Instead, the computer uses a Taylor series to turn that complex function into a long polynomial and then simply adds and multiplies to give you the answer. In physics, they simplify impossibly difficult equations, like creating a small angle approximation for a swinging pendulum. Without Taylor series, modern numerical analysis, computer graphics, and physics simulations would completely grind to a halt. We have covered a lot of ground today. Let us reinforce the key takeaways. First, a Taylor series is a mathematical tool that translates complex, difficult to calculate functions into simple polynomials. Second, it achieves this by extracting the function's derivatives at a single center point, using them as building blocks to recreate the entire curve. Third, while incredibly powerful, we must always be mindful of the radius of convergence, as the approximation is only valid within a certain distance from the center. By mastering this expansion, you now have the ability to approximate almost any smooth phenomenon in the physical world using nothing more than basic arithmetic. Great job following along, and keep practicing.